Okay, let's start. So in the last class we basically saw that all the single stage OTAs that we have seen so far, we can approximate them as a first order system, which means that if you finally use them in negative feedback, you are almost guaranteed that they are stable. But the issue was, or what was the issue with single stage OTA? Yeah, you can't drive a resistive load, especially small resistive loads. So that basically made us to go to the wherever the multi-stage OTA is, yeah, something like this, where the bulk of the gain you get from the first stage, and then you have the last stage specifically for driving the load. But the moment you have such multi-stage structure, we saw this is no longer a first order system, it's a higher order system, so we can no longer make any comments about its stability. So that led us into this journey of understanding stability, and we basically saw that if you have a first order system like this, say A0 by 1 plus S by P1, and if you use it in negative feedback with a feedback factor of beta, the loop gain is basically beta times A of S. And what was the unity loop gain frequency? It was beta times A0 times P1, right? And this was also equal to the closed loop bandwidth. This is also something we saw. Great. So now in a first order system, how did we convince ourselves that it is always stable in negative feedback? I mean, in the last class we saw that it is first order system is stable in negative feedback. How did we convince ourselves of this fact?
We consider only on the left side first order, and there is a negative feedback.
Yeah, I mean, basically we computed the closed loop poles, and we saw that it is always in the left half of S plane, and that's how we guaranteed stability. So the closed loop transfer function, if I were to write it, this is 1 by beta times the loop gain by 1 plus loop gain. So the closed loop poles are the roots of this equation, and for a first order we found it is always in the left half of S plane. So we saw it stable, right? But of course, if it's a higher order system, it is not trivial to find the roots of this equation. So every time you can't simply find the roots of this equation and check if it is in the left half of S plane. So that's why it's nice to, if you can make any comments about the stability of the closed loop system just by looking at the loop gain, right? And I'm sure you guys know some techniques. What are some techniques that help us do this? Yeah, okay, let's say an Nyquist plot. What else? I mean, they are metrics, but what are some techniques that help us? Let's say root locus, and one of you also told Bode plot. Okay. And typically I would say this is the order in which the complexity of sketching each of it increases, right? And usually these two guys give you exact information about the closed loop poles, but it is much easier to sketch Bode plot. So we typically try to understand stability using one of these and then translate that understanding to Bode plot so that we can make our life simpler. Although in most, typically it's done using Nyquist plot, I will try to do using root locus, because to convincingly explain Nyquist plot, I have to explain you complex analysis, Cauchy's integral, Riemann zeta function, number of encirclements in this side, that side. But as we'll see, root locus is more logical and intuitive. So let me take that approach. So let's look at root locus. Again, the point of the course is not make you understand and sketch root locus plots. I'll use it as a tool to make some comments about stability, and that's the final takeaway. At the end of this, if you're not able to convincingly sketch root locus, it's completely fine. That's not the point. Okay. The final point is the takeaways that we'll have from the discussion. Okay. And as you know, root locus gives you information about the closed loop poles, which are the roots of this equation. So the equation is 1 plus loop gain is 0. Oops. and I'll rewrite it as 1 plus beta times a of s is 0, and in turn my open loop transfer function I'll write it as a DC gain times the numerator by denominator. So this you can indeed rewrite it like this. Okay. So root locus essentially tells you how the roots of this equation varies as you vary one of the parameters, say typically the DC gain A0, right? That's the point of this. So it basically gives you how closed loop poles change as you vary A0. That's the whole thing. And yeah, I mean, I'll not go into a lot of details. We'll just make some logical observations from this and then try to get a qualitative sketch of root locus. Okay. So what I'll do is the following. Let's make some two simple observations. Now I plan to vary the DC gain from 0 to infinity, let us say. If I put A0 as 0, what happens to the equation? It reduces to basically d of s 0. So what are the roots of this d of s equal to 0? They are the open loop poles, right? So that's the first thing. You can simply say, I'll say closed loop poles are at open loop poles. Similarly, if I tend this guy to infinity, what happens to the equation? The second term is much larger. I can approximate it as n of s to be 0, right? So then what can you comment about the closed loop poles? They are the roots of n of s equal to 0. They are the open loop zeros. So that's one simple observation we can make. As you vary the DC gain from 0 to infinity, the closed loop poles or the root locus starts from the open loop poles and they terminate at open loop zeros, right? With simple observation. Second observation I want to make is the following. Now this is the equation whose roots we are trying to find. So this is basically, yeah, let us say I will make this. So let us say a point S0 could be a closed loop pole, let us say. So then I will basically write -1. So which means what can you say about the phase at that value? Huh? Yeah, I mean, okay, -180 plus 180, it's all tomato, one and the same. Okay. Right, so this means that at wherever the root locus is, if you evaluate the phase at that point, it has to be -180. So do you remember what does it translate to on the I mean what does it translate to with respect to root locus? Do you remember? Okay, so let me take an example. Let us say I am sketching the root locus, so it's the complex S plane sigma j omega. Let us say it has some 3 poles, for example. Let me say, I don't know, let's say -1, -3, -5, something. These are the open loop poles. Now let us see if you can make any comments about the root locus lying on the real axis, right? That is, let me take a point somewhere here. I will not use I mean, this transfer function I can write it as some A0, let's say A0 hat by s plus 1 s plus 5, right? So let me take a point in this section. So let's say that is some, I don't know, -8 or something, right? So if I evaluate the phase at this point, it has to be -180. So which means if I put -8 in this equation, the resulting value must be real. And what can you say about the sign? Its angle is 180, so it should be a real number, but what should be the sign? It should be negative. Fine. Okay. So let's try to see, right? If I put -8 here, what happens to this term? Is it negative or positive? it's negative, this is, so overall you get some negative term. So for some value a naught hat, you can make it equal to -1, right? That's what you want. So definitely -8 can be a closed loop pole for some value of a naught hat, and for that matter any point in this thing will, right? So what about, let us say, this section? Let me take some point in between, say it's -4. If I take -4, first term is negative, so overall it's positive, so this cannot be a closed loop pole for sure. So then can you generalize the observation? So what about this point, this section? We can again say it can be. So what is the logic? Yeah, basically number of folds, and in fact number of zeros also. I mean, I can also take something here, doesn't matter. So on the real axis, if you need to have the root locus, it means you need to have odd number of poles and zeros to the right. These are the two, I mean, simple observations actually, right? I'll just use these two to get a qualitative sketch of typical root locus plots. So first observation is you start from open loop poles and end at open loop zeros. Second is on the real axis you need to have odd number of poles and zeros. Okay. So let me take some simple case. Let's start with a system which has one pole. So this is the S plane sigma j omega. So let us say this is that pole. So once again we saw the root locus starts from open loop poles and end at open loop zeros. Where is the zero for this system? Infinity. So basically it can go to infinity along the real axis or in this complex S plane. Let's figure out if it can be lying on the real axis. Can it lie on the real axis here? We have odd number of stuff. So basically it will go to minus infinity like this. Simple. So now you see that the closed loop poles for a first order system, where is it lying? Yeah, real axis, but with respect to stability, it's definitely in the left half of S plane. So for any value of DC gain you choose, the first order system in closed loop is definitely stable. This is again another way of observing the same thing. Cool. So now let's add one more pole. Let me take two poles. So sigma j omega. Let us say these are the two poles. So again the root locus will start from open loop poles and they will terminate at open loop zeros. And where are the zeros here again? Infinity. Once again it can go, infinity can be on the real axis or in the complex plane. So first let's figure out the portion on the real axis. So can you have something here? So you can have only, so which means this pole is approaching somewhere like this. So now it cannot go to infinity along the real axis. Where can it go to infinity? Yeah, it will entire S plane. It's 360 degrees we have. So what will happen? Yeah, I mean basically it's simple land division problem, right? You have this entire land, you have two siblings, you have to divide it. You have to divide it equally. So this guy will go, this guy will take the, this guy top half, and the other guy will take the bottom half. So I mean just let's not worry about what is this point and stuff. Just a qualitative sketch based on logic and intuition. Okay, so now can you say if a second order system, will it be stable or unstable? It will definitely be stable once again, right? But the issue is, if you, as you see, if you have a large DC gain, the poles can lie on the S plane, the closed loop poles. So let's say they are somewhere here. So which means you have poles of the form minus sigma naught plus or minus j omega naught, right? So which means if I apply a step to the closed loop system, yeah, ideally I would have wanted some nice, let us say, exponential settling like this. But now if I have poles on the complex plane, how will the step response look like? Yeah, it will have some sinusoidal ringing portion, right? Okay. Magic, yeah, okay. Something like this. Right. Right. This is okay, yeah. So this corresponds to the omega naught sinusoidal frequency, and this minus sigma naught is the exponential decay you see. Okay. So that is why, I mean, although this is stable, you don't want your step response to show a lot of ringing most of the time. So which means, where do you want your closed loop poles to lie on typically? If you want to have any kind of ringing in the step response, you prefer your closed loop poles to lie on the real axis. Okay, so maybe I'll write it here. If you want to avoid ringing, closed loop poles great. So now we have been looking only at poles. Yeah, 0 should not feel bad, so let's add a 0. So I'll take the same thing, push it down maybe, sigma j omega. So I'll take again 2 poles, 0. So once again it will start from open loop poles and end at open loop zeros. So one of the poles will definitely terminate here and the other should go to infinity. So we'll figure out the real axis portion. Can I have something here? We have odd number of poles and zeros. I can't have anything here. The thing. So again, if you think about it, if I didn't have the 0, or let us say the 0 was very far apart, that it's close to infinity, the root locus was doing this. If the 0 was indeed at minus infinity, it would have kept going here and here. But now I know for a fact that one of the roots should terminate here, other should go to infinity. So what do you think will happen? The only logical solution is for it to come here like this, go like this. Okay. So if the 0 was very near, it might do quickly. If the 0 is far apart, it might branch out and take long time. Okay. So now if I have a large enough DC gain, what happens to the closed loop poles? They lie on the real axis. In the earlier case, if I kept increasing the DC gain, both the poles were going into the complex plane nicely. But now the moment I added a left half plane 0, the 0 has brought the poles back and made it fall on the real axis. Right? Cool. So now let's up the ante. Let's take 3 poles.
So does the ringing in the step response, like if I increase the DC gain, first it will increase and then after some time, after some value DC gain, it will start decreasing.
Correct. Exactly, right. So for this values of DC gain, you have significant ringing. This is the direction, and after some value, which is this one. So now let me take 3 poles. Yeah, okay. Let me, 1, 2, 3. So once again, it will start from this point and go to infinity. It can go to infinity along the real axis or in the S-plane. So it's trivial to see. This will be the real axis portion. Okay. So now again, they have to go to infinity. one of them is going along the real axis now. See, other way to look at it is we have 3 poles now. Again, 3 brothers, 360 degrees. How do you divide it? 120, 120, 120. So one of them will take this. So basically, this section is for one guy, like this. So, okay. I mean, I'm not going to a lot of details what this point and all, but at least intuitively it makes sense that this is how it might go, right? 3 poles, it has to go to infinity. S plane is there, you split it equally. That's all. Right. So now let's consider this case. Last case I will consider 3 poles and 2 zeros. Once again, so for a third order system, do you think it is stable or unstable? After some DC gain, let us say, I don't know, I'll call this A naught prime, let us say. After some DC gain greater than A naught prime, the closed loop system is definitely unstable. Okay. So let me now take the last case. One, two, three. So now we have 3 poles and 2 zeros, which means 2 of the poles will terminate at these 2 zeros and one will go to infinity, right? So let's again, if you sketch the real axis portion, you will have something here. Fine, correct, right? Yeah. So once again, the way to easy way to imagine is assume that the 2 zeros are much far away. You can assume that they are at infinity, which is this case. In this case, what happened? The root locus started to branch out like this. So now you have added the zeros, which means they can't keep branching out to infinity here like this. Yeah, one of them has to terminate, I mean 2 of them have to terminate here, and this guy, as you see, is nicely going and reaching the 0 here. So which means of these 2, one of them has to come here, other has to go there. So what will happen? They have to fold back. So once again, depending on the location of 0, it can actually cross over to the right side and come or not, but I'll take this case. It's okay. Yeah. If the zeros were very close, it might not even enter the right half plane. It might immediately do this, right? Again, exactly whether it will happen or not, lot of calculations you have to do, but typically this will be the case. Whether it will go to right half plane or not, that we are not sure yet, but let's consider a case like that. Okay. So the usual analogy I give for this is, poles are like naughty kids. If you have a lot of kids at your home, it's very difficult to control. They become unstable like this, right? And the moment you have adults, they fall back in line, right? So poles are like naughty kids, and zeros are like strict parents. If you have strict parents at home, no one is unstable. So the zeros are basically acting like some kind of magnets. So although the poles were trying to go away, it kind of attracts it and brings it back, right? So this is something we observed here also in the 2 pole case, right? So that is something we can comment on. If you have left half plane zeros, it might help you in making the overall system stable. You can sketch what happens there. Let us say you do this, something like this. You can sketch out. I mean, same logic, right? But I will take this case to make some points. That's all. So So let me actually take this. Yeah, so this is basically, we have 3 poles and 2 zeros. So here we know how to say if the system is stable or unstable, but we don't want to keep drawing root locus for everything. What do we want to draw? Bode plot, because we like Bode. So we'll try to sketch Bode plot of this and translate whatever understanding we had from this to the Bode plot. So let me sketch it here roughly. Let me sketch the magnitude of loop gain. So let us say this is for some DC gain A naught hat that I am sketching. So we have first one pole, then it falls as minus 20 dB per decade. Let us say we have second pole minus 40, third pole let's say minus 60, and then we have 2 zeros. So 1, 2. Just a rough sketch. Let me also mark these points. Okay, done. Let's also sketch the phase plot.
So for this beta times A naught hat, where is my like?
Yeah, we don't know. Yeah, we have not shown that this could be anywhere. This is for some value of A naught hat. We'll come to where it could lie later.
Where on this yellow line thing?
So it can be the closed loop poles are some. I mean, the A naught hat can be somewhere here. We don't know it. Right? This is variation versus DC gain. This is for some value of DC gain. This.
We don't know where the DC gain is.
Yeah. So I'll sketch the phase plot also. So if I have only one pole in the system, how will the phase plot look like? Just one pole. Let us say this is the case. I'll put as j omega. For omega equal to 0, this term is not there. What is the phase?
0.
As omega tends to infinity, I can neglect 1. What is the phase?
Minus 90.
So it goes from 0 to minus 90. I have 3 poles here. So where will the phase try to go to? Minus 270. So let me write it here. I have 3 poles. So it will try to go to minus 270. But I also have 2 zeros. What will be the phase added by the 2 zeros? It will be plus?
90.
No, 1 zero is 90, 2 zeros? 180. So finally it will tend to minus 90. It will start from 0. It will try to go to minus 270. And then the zeros will add 180 degree phase shift. And as omega tends to infinity, this will be the phase. Fine. So let me sketch it qualitatively. This is minus 90. Okay. So yeah, let me see and sketch it like this. Sorry, 0, right? Something like this. Okay, just a rough sketch. Okay. As omega tends to infinity, it goes to something like this. Very rough sketch. Good. So let's try to understand stability from root locus. Let me mark it here. Let me consider this point where the DC gain is say some A naught prime. Okay. So what can you say about the closed loop poles for this value of DC gain?
They are on the j omega.
2 of them are on the j omega axis exactly, right? So which means, maybe I'll erase it. This is, hopefully it's clear. So yeah, once again, so this is the closed loop pole. I mean, this is the equation that we are trying to solve to get the closed loop poles. The roots of this can be a complex number, but for DC gain A naught prime, two of the poles are exactly on j omega axis. There is no real portion. So which means even if I substitute s as some j omega, let's say some j omega naught, it will be 0, right? So which means this is something you guys know. What is the magnitude at that frequency? What is the phase? Yeah. Right. So now let's vary the DC gain here and try to mark a Bode plot corresponding to A naught prime, right? Is that okay? Now if I change the DC gain, what will happen to the magnitude plot? It will shift up or down, that's all. It's just going to get scaled. What will happen to the phase plot? Nothing will change. It's just a scaling in magnitude. Phase will remain the same. The magnitude plot will scale up or down, right? And for this value of DC gain A naught prime, I know that when the phase is minus 180, magnitude must be 1. So phase is not going to change. So let me look at the phase minus 180 somewhere here. So at this point the magnitude must have been 1. Let us say, okay, this is the, like how you guys make readings correct. We'll make it like this. Huh? This is where we have the 0 dB line, let us say. So I'll have to scale the plot so that something, okay, and then you have the third pole, blah blah blah. So this is some beta times not prime. I basically scale the magnitude plot so that when the phase is minus 180, I have basically made sure that the magnitude is unity. So fine. Now let me take another interesting point, A naught double prime. What can you say about the closed loop poles for this DC gain? Huh? They are again on the j omega axis, just like how we had for A naught prime. So same conditions will hold good here also, right? So which means when the phase goes to minus 180, which is happening here once again, the gain must have been unity, right? So I'll scale that gain again. So okay, it's not very nice, but yeah, something like this. Okay. Right. So why do you think I've considered these 2 points? When the DC gain is between A naught prime and A naught double prime is when the closed loop system is unstable, right? So that is the point of interest. So for A naught prime less than A naught less than A naught double prime, we definitely know that this system is unstable. Okay, so let's try to understand from Bode plot what's happening in this region, right? So this is A naught prime, A naught double prime. So all magnitude plots which will lie here, they will correspond to an unstable closed loop system. Is that okay? So we just have to make a simple observation now. When I keep, let us say, I mean, first of all, how did I get this point A naught prime? Or how did I sketch the plot for DC gain A naught prime? Yeah, when the phase was minus 180, I made sure magnitude is 1. Same for this guy also. Now I know that this is my, any magnitude plot in this range is an unstable closed loop system. So I should be looking at this point. So what can you say about the phase? Or to make it more clear, let us say I'll take some magnitude plot here. Okay. Right? I know that since this magnitude plot is lying in this unstable region, the closed loop system is definitely unstable. So can you make any comments about the phase? Yeah, basically in this region, any magnitude plot you have, if I look at the corresponding phase where the magnitude becomes unity, what can you say about the phase? It is less than minus 180 or magnitude is greater than 180. Right? Is that okay? So these are the boundaries, right? any magnitude plot lying here corresponds to an unstable closed loop system. So which means if any magnitude plot is lying here, when it goes to unity, the phase is much greater than, magnitude is much greater than 180. So now we know the condition. We just have to look at the, I'll say, magnitude of the phase, so that minus confusion is not there, of the loop gain at what frequency? At what frequency I'm trying to find the phase? The frequency where the loop gain becomes unity. This is the magnitude of the loop gain. I'm trying to find the frequency where the magnitude is unity, 0 dB. Is that okay? So this is omega u loop. This is the notation that we have used. So if the phase is greater than 180, then it is definitely unstable. Okay, that's all. Is this clear? I mean, I have just taken this root locus, tried to sketch the corresponding Bode plot. I have taken these 2 points because here is where I have unstable region. And as we saw, if I change the DC gain, only the magnitude plot scales. So these are the 2 magnitude plots for which the poles lie exactly on the j omega axis. So any magnitude plot in this region is definitely unstable. And I saw that for these magnitude plots, whenever it crosses unity, the phase of that loop gain is much greater than minus 180. So the condition I have to look for is, first I will find the unity loop gain frequency, find the phase at that frequency. If that is greater than 180 in magnitude, I can definitely say that it is unstable. Okay. So now let's look at this gain, A naught hat. So for A naught hat, this is the magnitude. So it becomes unity here. Yeah. So if I check here, the phase is so much. It's stable or unstable? Stable, right? And what is this difference called? Yeah, this is phase margin. Yeah, I'll call PM, not Prime Minister, but phase margin. Fine?
So here this 1 plus L of j omega will be 0 for 2 omegas, right?
Correct.
So omega 1 and omega 2.
Yeah, but it's plus or minus j omega, right?
Okay, sir.
No, basically this loop gain, this is for some DC gain A naught prime, right? For some, let us say,
Omega naught is minus j omega naught and some plus j.
it's a real system, you'll have complex conjugate poles, right?
That is just a single.
Yeah, so here is one pole, here is the other pole. Similarly for A naught double prime, one of the closed loop poles is here, other is here.
Omega 1 and minus.
So the takeaway is this: if you want to make any comments about the closed loop stability, you first find the unity loop gain frequency. That is where magnitude of the loop gain is 1, and then you compute the phase margin as 180 minus, to get rid of the negative confusions, I'll just take the magnitude of the phase. And this has to be greater than 0, and if it is greater than 0, we'll typically say that the system is stable. Okay. Cool. So now, if you understood it correct, let me ask you this question, because I usually ask it. So let's say I have a case wherein I find that for my loop gain, at some frequency the phase, let us say at some frequency omega x, the phase of the loop gain is minus 180. And at that same frequency, let us say the magnitude of the loop gain is say some 10, much greater than 1. Can you say if the system is stable or unstable? Can you think? Why? Okay, let's come to that. Anyone saying for stable? Anyone wants to make the system stable? Why?
Minus 180, it can go up or it
Yeah, so both of you are partially correct. See, the point is, the only thing that we know is this: when the magnitude is 1, if the phase is greater than 180, it is unstable. So the information I know is the following. If I sketch the phase plot, I know at some frequency the phase is minus 180. Let us say that is this omega x. And at that same frequency, if I sketch the magnitude is say some 10. This is that thing. Now if I increase the frequency, typically the gain is going to drop, right? So at some point it is going to come here. I just need to check what is the phase at this frequency. Now we can have two possibilities. It can continuously keep reducing. If this is the case, it's definitely unstable. But I can also have a case where the phase increases. Then it will become stable. Okay. So the correct answer is, you cannot say. Information is not enough. Okay.
That is like minus 20 dB per decade, then I can say.
We'll come to that later. The only thing is phase margin, that's all. Right?
If you can have some zeros to the right of that thing, it will rise up.
Yeah, that's all. The point is, if you have only poles, you are guaranteed that the phase will continuously reduce. Then you can definitely say it's unstable. That is, if I give you one more piece of information, that in this loop gain, there are no zeros, only poles, then you can guarantee that this will be unstable in closed loop. But if there are left half plane poles, left half plane zeros, that is important. If you have left half plane zeros, the phase will start rising. Let us say you can have zeros here somewhere. That will start increase the phase, and it can make it stable. Okay. So
if it is a high pass filter, then this calculation preferred.
What is high pass filter?
Means LSJ
Mm-hmm.
is open loop gain.
Correct.
Is
Oh, you're saying it's increasing. See, typically you'll never have a case where it always increases, right? You'll have some parasitic capacitor somewhere that will bring it down. You never have a true high pass filter as such. You can only have a band pass filter. You can't have a system which is having unity or some constant gain across infinite frequencies, right? At some high frequency it will drop. And for stability, you just need to check when it drops to unity, what is the phase. For example, it can so happen that it does this and then goes up, but eventually it will come down. Wherever it comes down and drops to unity is where you have to check the phase, right? Okay, that's what we have seen. So if you have a scenario like this where when the phase is minus 180, the gain is much greater than 1, you can say that it is unstable only if you have only poles in the system. I'll say only for all pole systems. Unstable not only for, I'll just say if it is an all pole system. Okay. No. Tell me.
Sir, for equal pole zero, pole and zeros are equal, then it not decay. You are saying that at last it will.
But the assumption that you are making there is something like this, right?
Yeah.
But you will never have a case like this, what I am trying to say. Because at high enough frequency, it can have it can happen. So basically, there are some cases where it can happen. If you have something like this, what will be the transfer function as t tends to infinity? Sorry, as omega tends to infinity. Let us say C, C and R. At infinite frequency, as very large frequencies, what will dominate in these two? Capacitor. So I can basically, at high frequencies, this is the circuit. So what is the transfer function? Half. Okay. So at low frequencies it will be 1, at high frequencies it will become half. That can happen. But there the only point is you have to check where it drops to unity. If it doesn't drop to unity, it's okay. Right? Yeah, you can also have a case like this. That is, if you have a direct feed through from the input to the output, That is some academic exercises, but in most practical systems you will never have a direct feed through from the input to the output, right? Here I am having this case because I have a direct high frequency path from the input to the output. So cool. So yeah, the takeaway is you check for this phase margin and see if it's greater than 0 to comment on stability. And if you are trying to design, now the question is how much phase margin is enough, right? And for that, let's look at some things. Or first, let me ask you this. Let us say for my loop gain, I find that the phase margin is less than 0. Can you comment on where the closed loop poles might lie? Sigma j omega. So most likely in the right half of S plane, somewhere like this. So if I sketch the step response, how it might look like? It will be sinusoidal, but the envelope will keep increasing exponentially, right? If I say phase margin is exactly 0, where the closed loop poles might lie? It will be exactly on the j omega axis. And how will the response look like, time domain response? Yeah, it will basically a pure sinusoid. And let's say phase margin is greater than 0 but not very large. Let us say it is some 5 degrees or something. Then where do you think the closed loop poles might lie? Left half of S plane, but can you narrow it down? Near the j omega axis, somewhere like this. So here, how will the step response look like? Yeah, it will ring, but that envelope of that ringing will decay exponentially, and that might decay slowly, right? So that is why it is not just enough to have phase margin greater than 0. You need to have sufficient phase margin, right? And how sufficient is, again, you can let's see. So you can decide on how much phase margin you want by actually looking either at the time domain response or the frequency response. So let's first look at a case with respect to the settling. Let me take a second order system for that. That might be easier to explain. So as we saw, if we have a second order system where we have only 2 poles in the loop gain, the root locus was basically doing this. Right. Now we noted that if you don't want to have any kind of ringing in the settling response, where do you want your closed loop poles to lie on? On the real axis. Great. But now you see that I can have the closed loop poles on the real axis, say somewhere here, or let's say very close to each other. Which do you think is better, or why? And let's say the gain is up to you. Let us say you are free to choose the location of the closed loop poles, right? So the question is, will I keep them apart like this, or I'll keep them close by? Why? Why critically damped?
Fast rising.
Yeah. Why is it fast rising? It's all correct. I am trying to ask you why more, so that you'll understand it better. Huh?
One is decaying fast and one is decaying slow.
Correct.
But I guess at the intermediate point,
that's the logic, right? See, if I have, as he's pointing out, if you have 2 poles, let us say the closed loop system has 2 poles, P1 hat and P2 hat, right? All my responses will have something of the form K1 e power minus P1 hat t. You want this to decay to 0 as soon as possible. Okay. Now, if let us say P1 is the low frequency pole, P1 hat is the low frequency pole, your settling will be dominated by this guy. If you want this to decay faster, you would want this P1 hat to be at a higher frequency. But if you keep moving this to a higher frequency, the other pole also comes lower. So what is the optimal point? Somewhere in the middle, where both of them lie bang on top of each other. Okay. the idea is I want my settling to be faster, and I know the settling is dominated by the low frequency closed loop pole, which means I want my low frequency closed loop pole to be at a slightly higher frequency. But the act of doing that also brings the high frequency pole to a lower frequency. So the logical point where you can get the best or fast settling is this. Okay. And what kind of damping is that? For a second order system, critically damped. Hopefully you guys remember that. That's where both the poles are at the same location. So if they are, let us say, apart like this, what kind of damping is that? They are real but not equal. It's called over damped, as you know. Okay. And what is the damping factor if it's over damped? Greater than 1. Okay, can check it, and usually I look at the quality factor, which is 1 by 2 times this guy. This will be less than half, and for critically damped this will be 1. So, and in fact you can actually work out. I'll give that as an exercise for you to work. What will be the phase margin for this? Does anyone remember?
76.
Yeah, it will be 76 degrees. It's a simple calculation. I'll give it to work out. So at this point the phase margin is 76 degrees. If the poles are here, the phase margin is higher or lower, do you think? Or let me ask you the other way. Let us say I have a case where the poles are lying here. Do you think phase margin is greater than 76 or less than 76? Less than 76, because it's on the imaginary axis, you are going to have a lot of ringing. So if I move like this, phase margin reduces or increases? Which means if I go here, so for an overdamped system, you will have a much higher phase margin, right? And in the limiting case, let us say you have this pole to be at infinity, then it looks like a first order system. For a first order system, what is the phase margin? First order system, we have only one pole. The phase will go at the max to minus 90 is the phase, which means you have 90 degrees of margin for the phase, right? So for overdamped, the phase margin is typically much higher, but with respect to the settling, this is a sweet spot. Can I take 5 more minutes? Okay, just finish it so that it's all relevant. Like I told, the other aspect to look for when deciding phase margin is the frequency response. And for that, let me quickly look at this. Let's say I have loop gain and a feedback factor beta. What is the closed loop transfer function? 1 by beta times the loop gain by 1 plus loop gain. Okay. If I say that it's a first order system, for example, let's start with that. Something like this. What is the unity loop gain frequency for a first order system? And this is also the closed loop pole, right? So if I, let me sketch it quickly. If I sketch the loop gain and the closed loop transfer function, the loop gain is going to look like this. It will start from beta a naught. When it encounters P1, it drops at minus 20 dB per decade. And this is the unity loop gain frequency. Okay. So on top of the same, if I try to sketch, let us say the closed loop transfer function. Now at low frequencies, how can you approximate the closed loop transfer function as? Yeah, I mean, let's say at DC, the loop gain is very large, so it's approximately 1 by beta, right? So let me take this case, and it's a first order system, and the closed loop pole is where? Same as omega u loop. Okay. If I sketch it, it will look something like this, and at this point, again, if you actually correctly plot it, it will have a nice curve like this, but Bode approximation, we don't do that, right? And this will be the 3 dB point, right? So that it's a 3 dB bandwidth. Okay. Right? So now let me see this. What is the phase margin for first order system? 90 degrees, right? If I say phase margin is 90 degrees, what can you say about the loop gain at the unity loop gain frequency? Yeah, this is, I mean, I'm not talking the angle or magnitude. It's a complex number, loop gain, right? Magnitude of the loop gain is what? Yeah. Magnitude of the loop gain is?
Minus j.
Yeah, okay. Magnitude is 1. Phase is?
Minus 90.
Phase margin is 90. So the phase is minus 90. So that's e power minus j. So this is minus j. If I were to now find the magnitude of the closed loop transfer function at the same frequency, what is that? Yeah, it's 1 by beta times I'll have minus j. So this is going to be, so this is again the unity loop gain frequency is the 3 dB bandwidth in closed loop if you have a first order system or if the phase margin is 90 degrees, right? This is another way to see the same thing. Now let me just take one other case. Let's say the phase margin is 45 degrees. Let us say now this is no longer a first order system. Let us say we have a higher order loop gain for which I find that the phase margin is 45 degrees. Then can you say what will be loop gain at the unity loop gain frequency? Magnitude is what? Phase is? Minus 1? 35? That's 3 pi by 4. So if you work out the magnitude of this at the same frequency, I'll make it work out. It will be greater than 1 by beta actually. Okay. It's again simple calculation. So if you sketch for this, it might look like this. At the unity loop gain frequency, you'll have a peaking and then drop. Okay. So now we can clearly see the 3 dB bandwidth is no longer at this point, it is somewhere here. Okay. So this entire business of saying that the closed loop bandwidth is approximately equal to the unity loop gain frequency is valid only if the phase margin is exactly 90 degrees. If you want to approximate it as the unity loop gain frequency, the phase margin has to be very high. If it's 90, this is exact. If it is not 90, it is approximate. Now it depends on how much you want to approximate. Okay. So again, this kind of gives you another indicator as to how you might choose your phase margin. In the closed loop transfer function, do you think I want this peaking or not? I don't want this peaking. Ideally, I want 1 by beta across all frequencies. Or if not, it should at least gradually reduce. So that gives you another indicator. You can choose a phase margin so that the peaking is not there. And typically at around what frequency do you think this peaking might occur? Around omega u loop is where that peaking typically occurs. Okay, not exactly, but around that. So you can basically constrain your phase margin so that the closed loop transfer function evaluated at the unity loop gain frequency is 1 or 1 by beta. Again, I will give it as an exercise. It's again a simple calculation. Whatever we did, it's a reverse calculation. So you can work out that this corresponds to a phase margin of 60 degrees. And for this, the the plot might look something like this. And the limiting case, let us say I have a case where the phase margin is 0. Then what can you say about loop gain? Phase margin is 0, magnitude is 1, phase is minus 180 e power minus j pi. It is. So if I put minus 1 here, what happens to the closed loop transfer function? Infinity, right? So it will basically shoot up to infinity like this. So if you have smaller and smaller phase margin, you will find more and more peaking in your closed loop transfer function. So if you want to reduce peaking, you better have more phase margin, and 60 degrees again a sweet spot if you want to keep this flat. Okay. So with respect to the fast settling, critically damped or 76 degrees something you can aim for. If that is not, that becomes too much, at least 60 degrees is the other number. So that's why you'll try to hit this usually. Okay. So again I'll stop here. Thanks.